Very honored to be here representing somewhat the space domain. I work at the European Space Agency. We have been developing for the last 30 years satellite navigation systems, and we have today made in Europe two very important operational systems, EGNOS and Galileo. They are both contributing to providing services to billions of users worldwide. And those systems rely very strongly on timing techniques, timing and frequency distribution techniques. So this is why I'm going to try to explain all of this in a short presentation. We have time and frequency needs in space missions, and the needs stems from different requirements. We need to generate signals from the satellites, which need to be stable or ultra stable. We need to tag those signals with time references, which are generated on board and very often synchronized with ground clocks. We need to, for some missions like exploration missions, we are flying satellites millions of kilometers away from the Earth into comets, stars, or far planets. And those satellites are not within visibility of the Earth, so they need to be autonomous from the timing point of view. And the requirements, as you will see, are very much tailored to the specific mission. So we don't have a standard way of generating time on board of the satellites. It depends very much on the type of mission we want to implement. So you see that there is a large variety, and this has led over the time to very different implementations. I have in the next view graph highlighted a number of key missions which are building on the generation of time in order to produce high-quality data. You see on the top left the Gaia mission. Gaia is today recognized to be one of the most powerful scientific missions, generating a lot of science data, actually exploring the universe, a precursor in a way to the James Webb Hubble telescope and James Webb telescope, a mission which is looking at stars and identifying far distant galaxies. And in order to do this, you need to, it is collecting data, and you need to time tag this data. If you don't do it, it is very difficult to recompose all this information back on the Earth and contribute to implementing the cartography, I could call it like that, of our universe. So you see on the view graph very stringent requirements with a rubidium clock on board, less than 17 nanoseconds over 6 hours, very stringent requirements at those orbits and altitudes. The ESA Cassini-Huygens mission, which was flying, has been flying for a number of years around the planet Saturn, and one of its moons, Titan, has also implemented on board rubidium clock technology for both the transmitter and the receivers, and this was also essential for the implementation of the mission. And you see on the right-hand side two missions, one US and one Chinese. The US mission Gravity Probe A, which was essential because it demonstrated for the first time the redshift theory of Einstein from space. This was also using very high stability clock, a hydrogen laser clock at the time. And I'd like to underline also the Chinese Mengtian mission, which was launched a couple of months ago, and it contributes to actually the Chinese space station. And it also implements very high accurate clocks on board. You see on the next view graph the European implementation of the equivalent of this Chinese mission in a way, which is what we call the ACES mission, Atomic Clock Ensemble in Spain. This atomic clock ensemble is composed of two types of clocks. One clock called the Pharaoh, which is a clock, an active major clock, which is providing very high short-term stability, and it will be, in my view, probably the most accurate clock flying in orbit. And this is combined with another clock, HHM, which is a laser-cooled cesium clock. I will not speak more about it because the next presentation will dwell on the implementation of optical clocks. And this mission, the ACES mission, is planned to fly in 2025. We have developed the Galileo system, which is one of the global navigation satellite systems around the world. And this system is operational. It consists of 28 operational satellites, and in each of them we have 4 ultra-stable clocks. We have clocks flying of 2 different technologies, passive hydrogen maser and rubidium clocks. So we have with Galileo more than 100 very high stable clocks in orbit. And this is an extremely powerful resource, which is being used in order to provide, of course, the services to the users on Galileo, but it also contributes very effectively to the international timing community. And I will explain a little bit why. Global satellite navigation systems, there are 4 around the world. The GPS, of course, also embarking very high accurate clocks. The Russian GLONASS system, the Chinese Beidou system, and the European Galileo. And they all are based on timing techniques in order to provide positioning services to users. Now, how does it work, satellite navigation? It is all about time. Basically, first of all satellites are synchronized to a system time. And this is based on atomic clocks. The satellite position and the clocks are estimated and are predicted by the ground mission segment. We have a very large, widely distributed around the Earth mission segment, which is actually estimating the clocks and predicting the time. And we have each satellite transmitting its own identification, position, but also the time and the health status as part of a navigation message. And finally, based on time measurements, the user calculates the distance to each satellite and then the own position of the satellite. Now, all of this is actually allowing the receiver to be very simple and low cost. And in fact, we provide the position, velocity, but also time information to the users. So you see that time plays a role in all facets of a satellite navigation system, and therefore we depend very much on universal astronomical time, on UTC, on leap second, and on all the issues which are being discussed in this conference. GNSS needs to be autonomous from the timing point of view. We need to provide the offset with respect to our own system time, but also the offset with respect to a universal time coordinate. And we also need to link to the Earth-based time on a reference system with high accuracy, such as the UT1 versus UTC offset. There is specific information on all those parameters, which is being provided in the Signal in Space interface control document, which is published for Galileo. And you see here 2 representations of those informations. The broadcast, which we broadcast to all the users, broadcast between the Galileo system time, the offset between Galileo system time and universal time coordinate, but also the offset between the Galileo system time and the GPS system time. This second offset is also very important because we want to ensure interoperability on the receiver level between measurements of the GPS signals and measurements of the Galileo signals. And we have, in order to provide for all of this, we have very accurate means of monitoring the time of the multiple GNSS systems. We have facilities which are deployed in our technical centers, which are monitoring in real time all the time parameters which are being broadcast by the different systems, which I mentioned before. Now, time could be easy, but we are facing on our daily life from an operational point of view a number of difficulties. First of all, we have to appreciate that universal time coordinate is an international recognized standard. But from the system operations point of view, we need to provide for a real-time and continuous time scale. And this is in order to implement the quality of our services. Now, the The synchronization to UTC in our systems is achieved by a modulo 1 second algorithms on ground. This is particular to Galileo. It's not done like that on the Russian GLONASS system, but it is done like this in the European Galileo system. And the varying number of leap seconds over time is something that we need to manage operationally. Last time we did it was in 2016, where we had to implement operational measures on our ground segments and on the message broadcast to the users in order to reflect the last implementation of the leap second. Now, nevertheless, each leap second introduction causes or can cause interruptions, because we had to actually very proactively, back in 2016, inform widely the whole international user community about the fact that we would introduce the leap second in our operations and in our message. And this is a perturbation, if you want, on the daily operations and the provision of the services, which can cause concerns. So this is something that we have experienced on user level, and some user receivers did not, in fact, correctly handle this leap second implementation. Each GNSS system time has a different tagging system of the seconds and a different way of broadcasting its own system time versus UTC. This is a fact. And there is also a different implementation of the leap second issue by the different systems, as I mentioned before, Galileo and GLONASS in particular. This is also creating a risk of interoperability between the systems, and is in fact creating a confusion or an uncertainty at user level, at receiver level. In addition, some user applications take directly the system time, which is computed by its own system, like a GPS or Galileo, as a reference for time tagging. This is done, for instance, by telecommunication networks or energy, gas, electricity distribution networks, which use GPS time or Galileo time for synchronization purposes. Also, financial transactions are done with time tagging very accurate to the nanosecond level, and those use also time references which are connected directly to GPS or Galileo. But it is a fact that each system provider creates its own time reference. And this is creating a multiplicity of time notions around the world, which is, in our opinion, an issue. In our view, GNSS operations, so the operations of GLONASS, Galileo, Compass, and Beidou, could be made more easy without leap seconds. I think this would be more straight to the users, and it would prevent transitions at user level and at the level of system operations. And also the possibility for, in the future, being confronted with what is called the negative leap seconds, which would reflect, in fact, a kind of acceleration of the rotation of our planet Earth, would cause a concern and maybe could be a source of confusion, since it has never been tested in reality. So let me just, in a couple of minutes, before I close this presentation, look into the future. We are going to implement in space, in future, better clocks. There are two instances illustrated in this view graph. The so-called Strontium optical atomic clock, which is being developed by Observatoire de Paris, CIRT, very close to this conference room, but also the NASA Deep Space Atomic Clock, which will fly in the future and will provide for unprecedented accuracies. We have also in Europe, and in the context of the Galileo program, a very large, very substantial program of development of new clock technologies, onboard atomic clocks that are going to replace in the long term rubidium and passive hydrogen maser clocks that we are flying today. And you have illustrations around this view graph of the different technologies. We are looking at technology diversity in order to be robust in orbit. We are also looking at a combination of technologies which provide very high stability in the short term and high stability in the long term. Both combined give us a lot of operational robustness. And you see a number of examples: rubidium 2-photon optical clock, iodine optical clock, rubidium pulsed optical pump clock, optical pumped cesium clocks, etc., etc. This is just to illustrate that we have a wide variety of developments going on in Europe, which are funded by European Space Agency and the European Union, and this will be the future of the onboard atomic clock implementation on our systems. So just to illustrate a couple of maybe inspiring missions that we are promoting these days, we will have next week in Paris also the ministerial conference of the European Space Agency member states, where 22 ministers of European countries will meet in Paris in front of Tour Eiffel for a couple of days in order to decide the budget for the European Space Agency in the coming years. And we are, as Navigation Directorate, coming up with two proposals of two quite innovative and far-reaching missions. One of them is Genesis. And now Genesis is a program which is implementing for the first time the co-location of 4 key different geodetic and navigation techniques on board of one single satellite. And this will allow for the co-localized calibration of the measurements of those 4 instruments, and it will allow for a very substantial improvement of the determination of the accuracy of the international terrestrial reference frame. We are looking at a very ambitious target of providing technical means for ITRF calibration up to 1 millimeter accuracy with 0.1 millimeter stability over the years. So this is a very fascinating mission, which is really looking into the future. And this mission can also contribute, because it will establish a very accurate reference of the terrestrial frame, can also contribute to observing or contributing to the calibration of the Earth rotation parameters, which is also indirectly very important for the discussions you are having in this conference regarding the long-term evolution of the time references in the world. And the second mission I wanted to highlight is Moonlight. Moonlight is about exploration. We had two days ago the launch of the Artemis launch by our NASA colleagues, but Europe is also on board. Europe is flying on that mission what we call the European Service Module, ESM-1, which is going to service the operations around the Moon and on the surface of the Moon. We are very proud of this initiative. This sets actually the start of a new era in the exploration of our natural satellite, the Moon, which will take place in the next decades. And those initiatives require, of course, good communication and good satellite navigation. So with Moonlight, we are proposing to implement the first communication and satellite navigation technology around the Moon and on the surface of the Moon. And this is actually very interesting because it is really a blank page. We are exploring a new planet, the Moon planet, and we need to recreate actually a reference frame for the Moon. We need to recreate a time, a universal time, I could call it, around the Moon, and we have to recreate all those notions. We are doing this in close collaboration with our NASA colleagues and a number of international partners. And I would like, you know, as you see in this view graph, a number of new notions, like timescale selenocenter, timescale moon surface, timescale moon orbiter, etc. We are confronted with a whole range of new parameters and new problematics which we are going to have to address in order to make the exploration of the Moon sustainable and in order to reach our objectives. And I would like, just as a conclusion, to propose a number of takeaways from my presentation for your consideration. First of all, a continuous timescale is very advantageous for any space systems operations. And you have seen the variety of space systems that we are implementing, and they all have their own specific requirements, but providing a continuous timescale is really necessary for all of them. Space systems need real-time timescales with a high level of continuity, availability, and reliability. So we need to pay a lot of attention to the technology. You have seen a number of examples of diversification of technology, and it has to fly in space, it has to be reliable operation in space. Space systems need to be synchronized to a recognized ground reference, like UTC. We are doing it with Galileo, providing offset parameters to UTC, offset parameters versus GPS, and this is all very important. Today, GNSS broadcasts a prediction of UTC, by providing with our real-time signals to users the offset parameters, and therefore we contribute in a way to provide a real-time universal UTC time service. The offset of universal time 1 to UTC is needed with the highest accuracy in the range of microseconds. We need in future better clocks with more stability and more accuracy, which can contribute to provide better GNSS accuracy. We need to work on robustness of all of this, of the clock technology, which is equally important for GNSS. And finally, for space exploration, which is really something to which we need to put focus in the future, needs to address the interoperability in the time metrology domain, also of the reference systems. And the involvement of the metrology community, which is represented here, is considered essential. And this is why I would like to invite the CGPM in order to maybe engage in future into some discussions and contribute to this universal endeavor to which ESA is fully committed in cooperation with our international partners. So thank you very much for your attention, and thank you again for this opportunity to address you all.